Okay, I guess I'll start. So thank you, Sri, for the introduction and the invitation to be here. So I'm talking on behalf of several current and former colleagues at Oxford. Names are given here. And so this is going to be more at the kind of application-focused end of these reduced precision talks. So there's not going to be kind of any proofs involving rounding error or anything like that. Okay, so why is reduced precision particularly appropriate for weather forecasting? Well, the main answer is simply that the model error for weather forecasts is kind of huge. So one of the main things a weather forecast model is trying to do is basically solve the moist compressible Euler equations. However, the domain is pretty large. It's the Earth, and therefore the solution's always going to be heavily under-resolved. And furthermore, there are many other processes going on in these models that's kind of important for the weather that you experience. So things like radiation, clouds, convection within the grid scale, and so on. And many of these other processes, they're also represented within the models, but only approximately, and indeed some of these processes are not represented at all. So there's a lot of model error to hide behind, and so it doesn't really matter so much if your individual calculations are less accurate. Just to drive this point home a bit further, so in fact, for the last couple of decades, most of the forecasting centers have rather gone away from producing just a single high-resolution best guess forecast, and instead they produce an ensemble of often slightly lower resolution forecasts where they try to capture the uncertainty in the forecast. So these ensembles are kind of multiple model runs that in fact don't just use different initial conditions, but they also use stochastic schemes within the models themselves. And this is kind of essential to get your model to spread out at the right rate. And so this is a ensemble forecast sort of from a few years ago now, but it is predicting the temperature at some point in the UK. So kind of across here is the forecast lead time, up here is the temperature in Celsius, and kind of the width of these boxes is kind of some measure of the uncertainty. And you can see how several days into the forecast, some of these ensemble members are predicting, say, 3 or 4 degrees, and other ensemble members are predicting more like 9 or 10 degrees. And therefore, the idea that each of these individual ensemble members is kind of calculating its state to 15 or 16 decimal places, it's obviously quite unnecessary. And indeed, it would be perfectly fine if you could have a lower precision ensemble that gave the same statistical properties as a full precision ensemble. Okay, so this is just a quick summary of kind of what's out there at the moment at an operational level. So there was some earlier work in our group from about sort of 6 or 7 years ago. So this Peter Dubin and Tim Palmer, and they showed that indeed it was feasible to take a full-scale weather model, and these were like all being done in double precision at the time. It was possible to take a full-scale weather model, turn it down to single precision basically everywhere, and it would give basically the same result. So several centers have now run with this. So Meteo Swiss, they use single precision operationally. I think they also run on GPUs. So they had quite a big model rewrite recently, which is why they've kind of adopted all of this newfangled technology. The European Centre, their model basically works at single precision, but they haven't quite made it operational. That will probably happen within the next year or so. The UK Met Office, they use single precision in just one part of the model. So that's the kind of single precision Krylov solver. So this is like the elliptic solve that's done each time step. And they indeed use that operationally. And in all of these cases, what they tend to observe is something like a 30 or 40% reduction in runtime for the part of the code that they've made, that they've turned from double to single precision. So, ideally you might expect 50%. Of course, not every part of the code is perfectly bandwidth limited or perfectly flop limited. Some bits are latency bound or operation bound. But 30 or 40% is still quite a significant saving. So That's going down to single precision, and we consider that to be sort of fairly safe. Modulo, sometimes you might want to do particular tweaks. There are some calculations you might want to leave in double precision. If you're pre-calculating something once but using it every time step, you can afford to use double precision, and so on, but the vast majority of the calculations you can do in single precision just fine. In a research context, we've continued to kind of investigate what happens if we try to go below single precision. And so this is sort of not at the level of a full model yet, but using kind of various either simplified models or individual kernels or routines from full models. Okay, so just before I go any further, so this is just a warning. So basically all the work I'll talk about from now on involves software emulation of reduced precision arithmetic. So there's various reasons for this, things like lack of language support, lack of hardware support once you go below single, especially bearing in mind that we're working with these legacy codes that can be, a few 100,000 lines of Fortran. You can't just kind of port that to GPUs or something very easily. Another nice thing is that by using software emulation, we're not just restricted to this kind of double, single, half, but rather we can investigate sort of bit-by-bit changes. But of course, since we're using software emulation, don't ask about speed up, because using software emulation is obviously a lot slower than just doing nothing at all. Okay, so the rest of this talk is going to be in two parts. So in the first part, I'll basically whiz through what a few other people in my group have been doing and present some highlight results. And then in the last few minutes, if there's time, I'll just sort of talk about something I've been looking at in a bit more detail. Okay, so this is probably the highlight result recently. So this is from Matt Chantry and Sam Hatfield, and this is all about Legendre transforms. Okay, so many of these weather models are what's known as spectral transform models. So they do some of their calculations in grid point space, so in physical space, and at some point they need to solve a differential equation. And kind of obviously one way to do that is set up a sparse matrix and solve AX equals B. There are models that take that approach, but in fact, most of the models do spectral transforms instead. So they do Fourier transform, Legendre transform into spectral space, do some calculations in spectral space, and then do an inverse transform back and do the various nonlinear calculations back in grid point space. So Fourier transforms, they come up in lots of applications. They're pretty well studied. Legendre transforms are a bit more specialized to this environment when you're working on a sphere, basically. However, it turns out that a Legendre transform is basically just a dense matrix multiply, and therefore it's very suitable for GPUs, reduced precision, and so on. So my colleagues looked at taking these down to half precision. One problem with half precision that I think Sri mentioned yesterday is that it's got a very limited dynamic range. So the biggest number you can represent is something like 65,000. However, these Legendre transforms are a linear operation, and therefore it's totally fine to take your initial values, rescale them to make sure that you're within the dynamic range, do your calculation, and then you can rescale them back afterwards. That's totally fine because it's a linear operation. Okay, so there's quite a lot going on this graph, so I'll just try to explain it. So this is showing the error, basically, versus a double precision run when you do these Legendre transforms at various levels of reduced precision. Okay, so so along the x-axis, this is the sort of simulation time of the forecast, so the error sort of tends to increase with time. This is, Z500 RMSE. That might mean something to like two other people in the room, but it's basically error. So one important thing here is this background shading here. So this is marked SPPT. So this background shading is a measure of the, SPPT is one of these stochastic schemes that kind of tries to add extra noise into the model as it's going along. And so the shaded region is basically an idea of what is the uncertainty in the model compared to, say, real life. And the high-level idea is that, if you're within the shaded region, then you can make kind of some sorts of errors here, and they're probably not going to affect the forecast too much. Whereas if you're outside the shaded region, then you're going to get a materially worse forecast. Okay, so the bottom line here is just doing these Legendre transforms in single precision. So this is all kind of the error with respect to a double precision run. So at single precision, that's all fine. You're well within the shaded region. Everything works. If you just kind of naively take it all down to half precision, then that's this line here, and that's sort of not quite good enough. So then these two other lines here, these are approaches where sort of most of the work is being done at half precision, but there's other kind of fixes going on. So one of them is this tensor core idea, where your input matrices that you're multiplying together are in half precision, but you're doing the accumulation at single. And that works out fine. And then the other idea, so that's this half trans 10 line. So these spherical harmonics, they have kind of different length scales going on. So the first spherical harmonic is just the global mean. The next spherical harmonics are like hemispheres, and so on and so on and so on. And this half trans 10 is basically taking the first 10 of these spherical harmonics and saying, we'll do those at higher precision, everything else we'll do at half precision. And this resolution, it's not quite operational resolution, it's TL511 if that means anything to anyone, but it's got something like order 500 or 1,000 spherical harmonics, and so keeping 10 of them at double precision or at higher precision, you're still doing the vast majority of the work at half precision. And then this is just kind of another graph showing similar information. So this is now the forecast error versus analysis, which is basically what happened. This is now at the operational forecast resolution, which is sort of slightly higher resolution than we saw before. And the double precision run, so that's like the reference one, is one of those, is sort of the middle line in there. And then these two ideas of doing most of the work at half precision, but with some fixes, they're sort of basically indistinguishable. Okay, so it looks like it's okay to do the Legendre transforms at basically half precision. So I'm now going to kind of go through a few other things. So my colleague Leo Safin was looking at reduced precision for the physics parameterizations. So this is basically the parts of the model that aren't trying to just solve a PDE. So this is not using a real weather model, but it's using something called SPEEDY, which is a highly simplified model. So here are a bunch of different physics parameterizations going on, so convection, radiation, et cetera, and he's looked at reducing the number of significand bits and in sort of these different schemes individually and doing the calculations at reduced precision. So 23 significand bits is already single precision, 10 significand bits is half precision, and you can see that you can reduce the precision of these calculations nearly all the way to 10 bits or so before you see any increase in the forecast error. My colleague Jan Akman, he's been looking at reduced precision preconditioners for a Krylov solve. So this is now just using a 2D shallow water model. So at double precision, it's sort of typically converging in 3 iterations or so. It's a very strong preconditioner. It's a sort of rediscretization of the differential operator, which is why it's only taking 2 or 3 iterations. If you just take this down to half precision naively, then kind of it now starts to stagnate, and you're no longer getting this good convergence. However, if you add in some fixes, so in particular he's using this nasty latitude-longitude grid where all of your grid points get really near each other as you go to the poles. So if you do some fixes like the points near the poles, you do those in double precision, everything else you do at half precision, then he kind of recovers the original performance again. And also my colleague Milan Klöver, so he likes to look at alternative number formats. So you might have heard of these things called posits, P-O-S-I-T. They're kind of an alternative to floating point numbers that have been proposed by John Gustafson. And I don't want to describe how they work here, but the sort of take-home message is that if your numbers are well scaled, so they're sort of order 1, then you can normally squeeze out a few extra bits of accuracy compared to a similar length floating point number. So this is just some kind of 2D shallow water simulation, quite simple. At double precision is the one in the top left. If you just use 16 sort of standard half precision floats, again emulated, then you get this one here, which is still kind of swirly, but it's sort of not quite evolved in the same way as the original one. Whereas if you use 16-bit posits, so here's a couple of different variants, then the evolution is sort of a lot more similar to the double precision floating point version. There's a couple of other variants here, but I'm not going to talk about those. Yeah, so just something I've been kind of working on recently. This is just some quite early work. So this is sort of less about floating point calculations, but it's more about kind of representing data more efficiently, particularly thinking in terms of moving your data between the main memory and the processor. You can argue that on the processor you can do everything in high precision because that's kind of free, but you're really being restricted by the memory bandwidth. So this kind of spatial data is not totally random. Nearby points are likely to have very similar values, temperatures, pressures, etc. And so an idea is to represent the function somehow as a sum of something on a coarse level that's perhaps more accurate, plus increasingly imprecise corrections. So I've written 32, 16, 8. You know, it could be whatever. So the same way that the previous work was all about kind of saying that the final bits of your floating point number are not that useful because they're not really representing real information. This is sort of targeting the initial bits and saying that nearby numbers are likely to have very similar initial bits in their floating point numbers, and so we kind of only need to represent those, say, once instead of 4 times. So my toy model for this is just 2D quasi-geostrophic equations. So this is just some like swirly fluid stuff. The details don't really matter. So this is the vorticity field that I've shown here. So obviously you can just reduce the precision uniformly straight away, so I kind of did that to give myself a benchmark to compare with. So I found that I could represent the vorticity field using, I've now switched to fixed point numbers because everything was kind of between -1 and 1, and so floating point numbers seemed a bit unnecessary. But I found I could represent the vorticity field using 16-bit fixed point numbers, and I'd get a normalized L2 error of something like 1%, which is small enough that if I plot them next to each other, I can't tell the difference. However, for this field, I found that I didn't actually get any benefit from this kind of multi-level representation. And if I go back, it should be kind of obvious why that might be, because this is a tracer field that's being advected with the flow, and so it's being stretched out into these like long, thin filaments, and therefore kind of it's varying quite a lot on the grid scale. But this quasi-geostrophic equations, so they also have a sort of stream function field going on. So you invert a sort of Poisson operator to go from the vorticity to the stream function, and then the velocity is the curl of the stream function. But anyway, the stream function field is obviously kind of much larger scale things going on, and it varies a lot less from grid box to grid box. And I found that I could represent this using just, say, 10-bit fixed point arithmetic to get the same sort of error in the vorticity field. But then if I switched to using a 2-level representation, I could use 7-bit fixed point on the coarse grid and 6-bit fixed point on the fine grid. And on average, that gave sort of a bit less than 10 bits, so 7-point-something bits per degree of freedom, which is a saving over kind of representing each number on the fine grid separately. Okay, so I'll wrap up here. So the conclusions, several centers are now heading towards single precision. Even there's sort of several projects going on where various centers are rewriting their models, and they tend to be kind of keeping the option open to switching to single precision at some point, even if they don't plan to do that straight away. We've been investigating the sort of the range between single and half precision in an academic context, and we're finding that we can go well into this range, even sometimes all the way to half precision in more limited parts of models, possibly with some fixes needed. Half precision, that often doesn't quite seem to be enough precision, so maybe hardware supporting somewhere in between might be desirable, whether that's sort of real hardware or sort of FPGAs that you can program on the fly and so on. And finally, there might be some possible benefits from things like posits and more efficient data representations in space and so on. Thank you.